So in section 7.2, we spent a lot of time talking about different types of trig functions in the integrand and how to integrate those. We went through sine powers of sine, cosine powers of cosine, and then combination of sine, cosine. And then we went to secant and cotangent and combination of those. We didn't do cosecant and cotangent just because it's huge similarities between secant tangent and cosecant cotangent. It's just usually a sign negative that appears in antiderivatives and derivatives sometimes. So that's the only one that we have to worry about. But other than that, the process and the technique is basically the same thing. So we didn't go through the cosecant cotangent process for that in that section. In this section, we are going to actually use those skills. We are actually going to be doing what we did for in the section of 7.2, but first we have to do something, and that's really what the idea is here in 7.3. So 7.3 is trying to help us do things where we have maybe we have powers of x under the radical or x under the radical, and radical is causing a problem or stopping us from doing something. Now, let me first step back a little bit and tell you radicals are not always bad. So if I have x square root of x squared plus 5, for example, dx, this is not bad. I can integrate this. I can do u equal to x squared plus 5, du is equal to 2x dx, and then 1/2 du is x dx. So it is 1/2 square root of u du, which is 1/2 is square root of u to the 1/2 du, which is 1/2, you get the idea, 2/3 u to the 3/2 plus c, and that's 1/3 u was x squared plus 5 to 3/2 plus c. So radicals are not always bad if you can do a substitution and there is a x sitting outside to help you with it. The ones that we're dealing with is situation either we don't have that x or we have other combinations that may not be pleasant. Now, another disclaimer here is some of the problems I do, you may feel like, well, I could have just done that with substitution, and that's totally fine, and you can do it. But if the question is to use trigonometric substitution, which is the topic of this section, then you ought to do it that way. And sometimes trig substitution just works nicer. Things work out very nice. So what's the idea behind trig substitution? Well, the idea is simple. And I do it with an example. Suppose somebody gives me integral of, say, x squared over square root of 9 minus x squared dx. So now, my first approach here is, can I do a u substitution? And if I do a u sub, I need an x on the top. I have x squared. So I have to do something with that extra x, which introduces a new radical at best. There's nothing else I can do, really. I would have to be thinking about other tricks involving that. So one thing that we realize is, well, I see a 9 minus x squared on the radical, and radical is really the part that I'm having problems with. So I ask myself, what would happen if x was, say, 3 sine theta? And bear with me, let's just go through this, see if this would make things a little bit easier. Now, if x was 3 sine theta, x squared would be 9 sine squared theta. Okay. And I'll explain how the 3 comes from and why did I choose sine and such. That's in a little bit. But right now, we have 3 sine theta for x, then the square of it would be 9 sine squared theta. But also, I have to change dx. And from here, dx is 3 cosine theta d theta. I get that differential for dx. So my top becomes 9 sine squared theta. The bottom is square root of 9 minus 9 sine squared theta times 3 cosine theta. So it's 9 sine squared theta. 3, let me actually take extra step. 9, 1 minus sine squared. Now you kind of see why I chose that specific. Now, not 1 minus sine squared is cosine squared. 9 cosine squared is absolute value of that comes out. But here's the thing. What if I pick my angle theta such that cosine of theta here turns out to be positive? And if I look at my unit circle, cosine is positive for values that fall in second or third quadrant. Sorry. In the first or my pen is over. If I want to get a positive cosine, then I want to be in the first or fourth quadrant, which means I should be between 0 to pi over 2 or 3 pi over 2 to 2 pi. Any kind of a branch that you pick would work, but again, you just want to pick a branch for which you will have a positive cosine. So if I say here, if I force my theta to be an angle between 0 and pi over 2, I'm excluding the pi over 2 itself because it will get 0 in the denominator. But if I get between 0 and pi over 2, then my angle, my cosine of the angle will be positive. And the absolute value would just be 3 cosine theta. Again, as long as your theta falls between either here or here, either between 0 pi over 2 or negative pi over 2 to pi over 2 to 0. So as long as your theta is between negative pi over 2 to pi over 2, you are in a good region because your cosine is going to be positive. So absolute value of it will just come up. Now, of course, these two can, this is now the easy part of it. You get 9 sine squared, which can be written as 1 minus cosine of 2 theta over 2. And then that can be integrated. Yeah, so that's basically just integrating 1/2 minus and then I get 9/2 x theta in this case minus 9/4 sine 2 theta plus c. But now I have to remember what theta represented. X is 3 sine theta. So if I have a triangle, and almost always you draw a triangle for these. If I have a triangle and this is my theta, x is 3 sine theta, or sine theta is x over 3. So x over 3 is sine, opposite over hypotenuse. And then the adjacent would be 3 squared minus x squared. So theta obviously is going to be sine inverse of x over 3. Now sine of 2 theta is 2 sine theta cosine theta. 2 and 9/4 cancel out, gives you 9/2. And sine theta is obviously x over 3. Cosine theta is root 9 minus x squared over 3. So that would be your antiderivative. So let's look at the steps that we took here. So there was a magical step we took first to decide what do I substitute x with. And then I made sure that not only I do the substitution for x squared, and then I do dx calculation based on the new variable theta. I plug them in just very clearly, just as it was. I plug them back in. And then I get to a point that I was able to get a perfect square and bring it out. And then when it came out as an absolute value. I said, well, let's make sure we choose our angles so the absolute value would be positive inside of the absolute value would be positive. So I wouldn't have any need for absolute value. So that's how that absolute value was removed. And then they canceled out the cosine. After this, it was just an integration of trig function. That's hence section 7.2. And then the last part, after I find the antiderivative, then I have to replace theta in terms of x, whatever x values are, which usually requires drawing a triangle based on your very first expression. And that's how we handle this. So I think now we're ready to talk about what substitutes for what situation. So we consider three different situations. The situation where I have some a squared minus x squared, I have x squared minus a squared, or x squared plus a squared, or a squared plus x squared. If I have a squared minus x squared, I want to create a situation like sine cosine combination. So I let x be a sine theta, because when you square it, becomes a squared sine squared, and you can factor out the a squares. For this one, I'm going to let x be a a secant theta, because then I get a square secant square. This is tan square. Again, opportunity for it to come out. And for this one, I'm going to let x be a tangent theta. So I get a squared tan square plus a square, which is a square tan square plus 1, which is secant square. Again, opportunity for that to come out. So these are the standard substitutions we're going to use for this. Anytime you have those situations, it doesn't always have to be under the radical to use trig sub, but being under the radical is a good reason to use trig substitution. But it's not always that. That's not the only reason we would do it. Sometimes we could use it for other things as well. Let's do another problem, and then maybe we can explain this better with another problem. So this is actually number 5 of your problem set. Page actually 7.3, number 5. So this one is integral of square root of x squared minus 1 over x to the 4 dx. So I'm gonna let x be, remember we're doing now this one, and let x be a, which in this case is 1, secant theta. Dx is secant theta tangent theta d theta, just a differential there. So it's going to be square root of secant squared theta minus 1 over secant theta tangent theta, over secant to the 4 theta times secant theta tangent theta d theta. Okay, so the secant and one of the secants cancel out. So I'm going to have square root of tangent squared theta, which is as planned, over secant cube theta times tangent theta d theta. Tangent squared, again, I'm going to make my angle theta to be in bounds where my tangent squared is positive. So I'm going to get tangent theta squared, combining these two, over secant cube theta d theta. Remembering tangent is sine theta over cosine theta, and secant is 1 over cosine theta. The 3 and this cancel out, so I get sine squared theta cosine theta d theta. This was one of the situations we had in the last section, so I'm going to let u be sine theta, du is cosine theta d theta. So I get u squared du, which is 1/3 u cubed, and u, of course, is sine theta. But remember, now I have to go figure out what is it equivalence of it is. So if this is theta, secant theta is x, secant is 1 over cosine. So hypotenuse over adjacent is x. So this turns out to be x squared minus 1. So here I have sine, which is opposite over hypotenuse, opposite over hypotenuse. And that's how you solve this. Okay. Yeah, you do have to take the final step to make sure that you are done with this process. Let's do number 12. And I'm not sure if I signed this for you guys, but let's do it anyways. So number 12 is the one that's the tangent now. And it is a definite integral. So we have a couple of things to figure out here, but I'll let you guys decide how to approach this. Now, one school of thought, when they see something like this, they're like, okay, you know what? First solve antiderivative of the t over square root of 4 minus plus t squared. Do that, find some solution to that antiderivative, then plug in the original bounds of 2 and 0 in there. Another school of thought is like, well, you do the substitution, then go ahead and change 0 and 2 at the same time. So you can do that as well. In fact, that's how I'm going to do it, just so you guys see how that process would work. And that kind of like goes around having to do the triangle for the most part. So because it's a plus, remember the identity for plus is tangent. So I'm going to say A is 2. So I'm going to let t be 2 tangent theta, which means when t is 0, theta would have to, tangent theta is 0, which means theta would have to be 0. When t is 2, 2 tangent theta is equal to 2, which means theta would have to be pi over 4. Again, 2 tangent theta is 2, which means tangent theta is 1, and inverse tangent of 1 is pi over 4. So I go from 0 to pi over 4. If t is 2 tangent theta, dt is 2 secant squared theta d theta. So I get 2 square secant squared theta d theta over square root of 4 plus 4 tan squared. Two secant squared on top. 4 plus 4 tangent squared is 4 secant squared. Square root of that is 2 secant. Now you don't have to do this and go back to your user triangles or anything. You can just go ahead and plug in the values, but let's finish this. From last section, I told you guys that antiderivative of secant is natural log of secant plus tangent. No, there was a derivation for that. So you get natural log of secant pi over 4, tangent pi over 4, minus natural log of secant 0 plus tangent 0. Secant pi over 4 is 1 over cosine pi over 4, which is root 2. Tangent pi over 4 is 1. Secant 0 is 1. ln of 1 is 0. And that would be your answer. You didn't have to go back to x and plug in 0 and 2. You just stayed with theta. Basically, they're all like this. There's not much going on there. But again, these are most of the problems will be at the level of having to simplify the expression, doing the integral of it, and then plugging back in or converting it back to x. Okay. Now, I see problems here that would require you could do substitution for them as easily. And you're welcome to do those with substitution if you wanted to. But if the test says, or the question on the test says that you have to use a trig sub, then you must use trig substitution for that. Okay. So I hope this presentation helped you understand trig substitution a little bit better. And of course, post your questions or homework problems that you want me to look at. And then maybe I can go through those with you and explain some of those for you as well. Okay, but this should get you started to be able to do the homework for these for this set. So thank you.